In this video, we're going to talk about the greatest common factor and how to use factor by grouping. To find the greatest common factor of a list of monomials, we're going to do the following steps. Step 1, we'll find the greatest common factor of the numerical coefficients. In order to do this, we'll use a factor ladder that consists of prime factors only. And if we write those in exponent form, it might help us to identify what the greatest common factors are. Step 2, we're going to find the greatest common factor of the variable factors. So that means what amount of each base is common to all terms. And finally, for step 3, we'll find the product of those factors that we found in steps 1 and 2. In our first example, we have two separate terms, 72x to the 6th y squared compared with 60y cubed. So we want to look at the numerical coefficients first. We'll start with 72, and the factor ladder simply means we're dividing this numerical coefficient by prime numbers. Since 72 is an even number, I'll start by division of 2. That makes 36. Again, we have an even number, so I can use 2 for my prime factor. 36 divided by 2 leaves 18. 18 is also divisible by 2, leaving 9. Since 9 isn't an even number, I have to choose some other prime number to divide by. So it looks like 3 would work. 9 divided by 3 leaves 3. And again, I could divide by 3, leaving 1. So you can see here in our factor ladder that we have factors of 2, 2, 2, 3, and 3. We'll do the same process for our other numerical coefficient, which is 60. So starting with 60, it's even, so the first prime I would try to divide by is 2. That leaves 30. Again, that's even, so I'll use another 2. 30 divided by 2 leaves 15. And since 15 ends with a 5, I know I could divide it by 5. That leaves 3. And 3, of course, is divided by 3. So here are the prime factors of 60. In order to build our greatest common factor, I'm making a comparison of the factors between 72 and 60, and I want to know what is in common. So I'll start by circling what factors are in common. So 2 is in common with 2. Here's 2 again, in common with 2. Is there another set of 2 that's in common? It doesn't look like it, so I'm not going to circle another 2. How about 3? It looks like each of these coefficients had a factor of 3 in common. Is there another factor of 3 in common? No. And then I have a 5. Do both terms have a 5 in common? No. So only the ones that I've circled are the factors in common. 2 times 2 times 3. 2 times 2 times 3. We could call that 2 squared times 3. That means 4 times 3, and that means 12. So for the numerical portion, I know that 72 and 60 have the factor of 12 as their greatest common factor. Now we also need to go back and look at any variables that are included. So with 72 we have base of x and base of y, and with 60 we only have bases of y. We don't have any bases of x in common, so I'm not going to even consider x in my greatest common factor. So with y squared, that means y times y. Y cubed means y times y times y. So to see what's in common, you can see I have a set of y, I have another set of y, but I don't have another set of y. So 2 different sets of y is y squared. So I need to be sure to include y squared with my greatest common factor. So 12y squared is the greatest common factor between our original terms. Now let's try the process over again in example 2. We're starting with 180. Since it's even, I'll divide by 2. That leaves 90. Again, that's even, so I might as well divide by 2. That leaves 45. That's not even, but it ends with 5, so I can divide it by 5. That leaves 9. 9 is divisible by 3. That leaves 3. And 3 is divisible by itself, leaving 1. Notice how every time we end up with 1 as our last factor, we are completely done factoring. So here are the prime factors of 180. 2 times 2 times 5 times 3 times 3. And it doesn't make any difference what order these terms are written in. Next, we'll work with the base 270. 270 is an even number, so I know that I can divide by 2. So 2 goes into 2 once, 2 goes into 7 3 times with 1 left over, 2 goes into 10 5 times. Now this also ends with 5, so I know I could divide by 5. 5 goes into 13 2 times, leaving 3. 5 goes into 35 7 times. 27 is divisible by 3, leaving 9. 9 is divisible by 3, leaving 3. And 3 is divisible by 3, leaving 1. So here are the prime factors of 270. What we're looking for now are the common factors. Here's a pair of 2's. Do I have another pair of 2? No. Do I have a pair of 5's in common? It looks like we do. Do I have a pair of 3? And we also have another pair of 3. So notice I did not circle every 3. Only this one-to-one correspondence will create your greatest common factor. So we start our greatest common factor with 2 times 5 times 3 times 3. Now it's nice when we put these in order from smallest to largest, so 2 times 3 squared times 5. So 2 times 9 times 5, and I know 2 times 5 makes 10, so 10 times 9 would be 90. So I'm starting off my greatest common factor with the numerical coefficient of 90. And then we go back and look at variables. So we have originally x is appearing in both terms, y is appearing in both terms. Starting with x's, you probably don't want to have to expand x 5 times and then 7 times. So one shorter way to work this out is first notice both have a base of x, and then whichever is the smaller exponent is how much of that base is guaranteed to be found in both of the terms. So I know to include x to the 5th. And then you can do a similar process with the bases of y. So both of the terms have bases of y. Comparing 8 and 4, 4 is the smaller, so that is what is guaranteed to be found in both of the terms. So we're also including y to the 4th in our greatest common factor. To find the greatest common factor of a polynomial, we're first going to write each term in prime factored form. Next, we're going to identify the factors common in all terms. And last, we'll factor out that greatest common factor. So if I write 15 in its prime factored form, I'm thinking about 15 divided by prime numbers. Since it ends with 5, I could divide by 5, and that leaves 3. 3 divided by 3 leaves 1. So 5 and 3 are the prime factors of 15. And then the similar process using 21. 21 is divisible by 3, that leaves 7, which is divisible by 7, and that leaves 1. So 3 and 7 are the prime factors of 21. So you might notice right away that 3 is a common factor for both of those terms. So to begin my factoring of this binomial, I begin with our common factor 3, and then check out any variables. Both have bases of x, so I'm getting ready to include x. Comparing exponent of 3 and 2, 2 is the smaller, So that's the amount guaranteed to be found in both terms. So although 3x squared is the greatest common factor, we need to include what the other factor is so that we have completely factored this polynomial. So the way we do that is what we call reverse distributive property. 3 has to be multiplied by something to recreate the original term. 3 times 5 would create 15. X squared then would be multiplied by how much to create x cubed? So here you have to think about product rule. X to the 2 plus 1 would match x cubed. Finally, we need to match our last term of negative 21x squared. So 3 would have to be multiplied by a negative 7 to create a negative 21. And you'll notice that x squared already is an exact match, so we don't need to include any more bases of x. So our final answer here in factored form is 3x squared times the quantity of 5x minus 7. In our next example, we have the polynomial of 8x cubed y minus 6xy plus 2x. So you'll notice this time we have 3 terms in this polynomial. We're first starting with the numerical coefficients of 8, 6, and 2. Since they're even, we know at least 2 is in common. And since 2 is our smallest coefficient, that's also a clue that we could never use a number that's larger than 2. So starting with 2, we'll then look at the variables, x, y, x, y, x. So it looks like all of our terms have at least x. Checking out the powers, 3, 1, 1. All terms have at least x. Notice that only the first 2 terms have base of y. The last term does not have a base of y. So 2x is the greatest common factor. Using the distributive property, we need to recreate the original terms to completely factor this polynomial. 2 times 4 would match 8. We have x, but we need x cubed. That means x to the squared power would match. And also, we don't have any bases of y, so we'll have to multiply by a base of y. So when you distribute 2 times 4, that makes 8. X times x squared, that makes our x cubed, and multiplication of y would match our last term y. So that looks great. We're ready to recreate the middle term now. 2 times something needs to match negative 6. So that would be negative 3. Compare x with xy. Notice we have x completely, but we don't have y. 2x times negative 3y would match negative 6xy. And finally, the last term. We started with 3 terms, so we must also have 3 terms in this parenthesis. It looks like 2x already matches 2x. They both are positive, so a positive 1 is the necessary placeholder. If you do not write plus 1, you would never be able to distribute and therefore create that last term. So positive 1 is a very important placeholder when factoring. Here is our completely factored answer.